Lines and rates of change are actually a very huge concept in AP Calculus. So I want to take some time to just review a lot of the algebra sort of stuff with lines and rates of change. As a definition, slope is going to be the amount of vertical change for each unit of horizontal change. Of course, you remember that we think about slope as being rise over run. More specifically, it's going to be the change in the y coordinates over the change in the x coordinates from one point to the next point. That's how we get that y1 minus y2. That's the change in y. And x1 minus x2, that's the change in x. So real quick, if we wanted to practice on a couple here, we want to find the slope between these 2 points. We would subtract their y coordinates, 1 minus 65, and then their x coordinates in the denominator, 2 minus 10. That leaves us with negative 64 over negative 8, which is a slope of 8. When we have 2 coordinates that are the same, in this case, the y coordinates are the same, so we'll have 5 minus 5 in the numerator, and then in the denominator, 4 minus 2. So since we end up with 0 in the numerator, that means the entire slope is 0. Now, if it is the x coordinates, maybe we have 3, 4, and 3, negative 9, and we wanted to find this slope, subtracting the y's in the numerator, and the x's in the denominator leaves us with 13 over 0. Whenever we have that 0 in the denominator, of course, we say that the slope is undefined, and that will be a vertical line then, whereas the slope of 0 is going to be a horizontal line. But here's a slope that's a little bit more interesting, that when we're trying to find the slope between these 2 general points, x, f of x, and some other point on the curve, a, f of a, then when we find that slope, we subtract their y coordinates in the numerator and their x coordinates in the denominator. Without knowing what f of x is, then we would end up leaving our slope just like this, which should be a pretty familiar fraction for you. Another way to look at it is we still have that same general point, x, f of x, but what if we change x somewhat by adding a certain amount of change to x? Then our second point is x plus delta x, and the y coordinate would be the functional value at x plus delta x. When we look at that slope, it's going to be y coordinate minus y coordinate. This time, I'm going to take the second coordinate, f of x plus delta x, and subtract off the first one, f of x. Then when I do the denominators, I got to take the x coordinate from the second point first and subtract off the x coordinate of the first point. We can simplify this a little bit. Just by canceling the 2 x's in the denominator, and that leaves us with delta x. This should be another fairly familiar fraction for you. And both of these fractions, remember, are talking about slope. And when we're looking at forms for equations of lines, I'm sure that you guys are Hall of Fame professionals when it comes to slope-intercept form. So the 2 that I want to bring up are point-slope form and general form. Point-slope form is actually going to be the most convenient one for us. That when we know one point and we know a slope, then we have everything we need to come up with the equation of a line. Just put the slope in for m, and then the coordinates in for x1 and y1. The general form, ax plus by plus c equals 0, that's more for making it look pretty. You know, where a, b, and c would be nice integers, a would be positive, they wouldn't have any common factors between them. So let's say we wanted to find the equation of line passing through these 2 points, 3, 5, and negative 7, 75. Well, there's only 2 things you need to find the equation of a line. That's a point and a slope. We have 2 points, so we need to find the slope. To do that, I'm going to subtract the y's in the numerator, 5 minus 75, and the 2 x coordinates in the denominator, 3 minus negative 7. That'll leave us with negative 70 over 10, or a slope of negative 7. But now that I have my slope and a point, and I can pick either of these points I want, I'll just take this one. we can write the equation of our line in point-slope form. Remember, point-slope form is going to be y minus the y-coordinate, which was 5, is equal to slope times x minus the x-coordinate. And that's it. All right? When I ask for equation of a line, that's the equation of a line. It's done. Unless I tell you to put it in some other form, you can stop right here. But let's put it in general form. To do that, we're first going to want to distribute the -7. And then bring everything over to the left-hand side. So I'm going to add 7x. And then I'll also subtract 21. That will give me that -26 on this side. And I forgot to add 7x, so showing that, we're left with 0 on this side. Looking at each of the terms, 7, 1, and 26, those coefficients in the constant term, they don't have any common factors. The leading coefficient is positive, so 7x plus y minus 26 is in general form. Here we want to write the equation of a line that's parallel to 2x minus 3y equals 5, but passes through the point 2, -1. So two things we need are a point and a slope. I have a point, I need to find the slope. To do that, we're going to have to rearrange 2x minus 3y equals 5. The best thing to do, I would say, is to put it in slope-intercept form first. So I will subtract 2x from both sides, and then divide everything by -3. Okay. Who cares about simplifying it? Because we can see right here is where our slope is, 2/3. So now that I know that my slope is 2/3, and we have this point, that's everything we need to write the equation of line. Y minus the y-coordinate is equal to slope times x minus the x-coordinate. Simplify that minus a -1 and we're finished. And of course, you can leave your answer in point-slope form. That would be great, actually. So, I don't know if you know this or not, but calculus was invented by two people at the same time, but completely independent of each other. The two people were a German mathematician. His name was Gottfried Leibniz. But then an English scientist, Isaac Newton. And yeah, it's that Isaac Newton. But he invented, when he was looking at calculus, he was looking at it in a purely scientific way. And one main characteristic of his perspective of calculus was looking at slope as a rate of change. And that was very important to him. Rate of change being just the ratio of two related quantities. So one way, an example of thinking about rate of change is like speed. Right? Speed would be a rate of change. And a common speed that you probably feel comfortable with is miles per hour. Now, miles per hour technically is miles per hour, like this. And when we're trying to calculate that rate of change, what we actually do is we look at the change in miles over the change in hours. And that's how we end up calculating miles per hour. That should seem very similar to slope, which we said was change in y over the change in x. All right? When we have the ratio of two quantities that are related, then we're talking about a rate of change. Actually, when I bring this up to my Algebra 2 students, I tell them that rate of change is slope, but with units, really. So if we look at this example here, in 2000, the population of Nevada was about 1.9 million people. In 2012, it was about 2.7 million people. Find the average rate of change in population over time. And then we'll use this rate to estimate the population in 2020. First of all, finding the rate of change. Go back to the question. It says find the rate of change in population over time. It's worded that way on purpose because when we're trying to find this rate of change, we need to know which quantity is going to go where. And this tells us we want to find the change in population over the change in time. To calculate that, all we have to do is see how it changed from 2000 to 2012. Well, in 2012, the population was 2.7 million people. To find how big of a change that was, we'll take away the starting amount, that 1.9 million. We'll do the same thing with time, that we'll match them up. In 2012 is when there was 2.8 million people. We'll subtract off the starting time, which was 2000. Now, when we calculate this, the difference in the numerator would be 761,000 over 12 years, which ends up being about 63,416 and 2/3. Now remember, there are units involved here. Right? When we're talking about rate change, we do have some units. And how do we measure population? In people. How are we measuring time in this problem? In years. So this is saying that the population in Nevada is adding 63,000 people every year. So when we want to estimate how many people are going to be in Nevada in 2020, well, that's 8 more years. So if we just take that 63,416 and 2/3, and we multiply it by 8, we end up with 507,333 and 1/3. So we'll say about 507,000 people. But that's how many people are added to the population from 2012 to 2020. So in 2020, there's going to be that 2.7 million plus 507,000 more, for a total of 326,333 people. So 3.2 million people. One last concept I want to talk about is the average rate of change. In calculus, when we're talking about the average rate of change, we're talking about from the beginning to the end. So on this interval from 2 to 7, what is the average rate of change? Well, when we look at these 2 points, we have 2, -2 down here. And up here we have 7, 13. To find that average rate of change, all we have to do is calculate what's that change in the y-coordinates divided by the change in the x-coordinates. Really, we're just finding slope. So 13 minus -2 over 7 minus 2 gives us 15 over 5, which is 3. That was finding the slope of a line. Once we have a curve, right, calculus students tend to get a little bit more weirded out. They focus on this average part, and if you try to be very direct about average and add up all of the slopes and then divide by the number of slopes, well, there's actually infinitely many slopes. Right? On a line, all of those slopes are exactly the same. But when we look at a curve, I mean, I got a slope of a tangent line here and here and here, and these are all different. But there's infinitely many slopes, and there's no way you could count them all, let alone add them all up and then divide by the number of numbers. But when we're finding the average rate of change, all we care about is the beginning and the end. And we really find the slope of this line between these 2 points, the secant line. Well, these 2 points are in the exact same spot, 7, 13 and 2, -2, which means that average rate of change is going to be the exact same slope, 3. Right? Because sometimes we have positive slopes, sometimes we have negative slopes, sometimes we got slopes of 0. They all kind of average themselves out to have the slope of this secant line. So if I want to find the average rate of change from 2 to 7, all we have to do is look at that secant line. This is the point 2, -1, and this is the point 7, -1. With that slope, -1 minus -1, over 2 minus 7, we end up with a slope of 0. That on average, its position didn't change. All right, that from the beginning to the end, the y-coordinates stayed the same. They didn't change at all. That means that its rate of change was 0 over that time period from 2 to 7. This idea of average rate of change is going to be very, very important. So what you need to do is to recognize that average rate of change just means the slope from the beginning to the end.